going to be talking a little bit about the actual experiment that we did and some of the results that we got, and also a concept called simple effective theory, which I will discuss later.
It's the down button.
Down?
Down. There you go.
All right. Okay. So I guess our whole story starts with the GlueX experiment, which Ryan discussed a little bit. And this experiment is going to be taking place at the Thomas Jefferson National Accelerator Facility in Newport News, Virginia. And here's an artist's rendering of what the facility is going to look like. And the purpose of this experiment is to study something called quantum chromodynamics. And you heard Ryan discuss the color force that binds the quarks in the atoms, and it's mediated by gluons. And that's basically what they're going to be studying with this experiment, as well as a concept called confinement, which is when quarks are combined in color-neutral groups called hadrons. And that's basically when three quarks, say, make up a proton or neutron. That's the basic concept. And here's the detector of the facility that you saw before. And for my talk, basically we are only interested in this portion, which is the diamond wafer. Now in the experiment, we pass an electron beam through the diamond wafer, which creates photons. Now these photons are later used to create mesons. And a meson is a quark and an antiquark that form a composite particle. And we use these mesons to study the nuclear glue that binds the quarks together. And obviously we have many collaborators on such a project, including many universities and Jefferson Lab, but also the University of Connecticut, which is where we come in. And here's the picture that you saw before of this mock setup of the diamond that we used in our actual experiment. And as you can see here, the tungsten wires are very thin, but you can perhaps see them. And just ignore this. This is a flash of the camera that we used for the picture. And we have a piece of glass standing in for the diamond. And you may be wondering why we have to suspend the glass on tungsten wires. Because if we were able to fix it to a frame, we wouldn't get these vibrations. However, we have an electron beam that's going to be striking the diamond. And you'd think an electron beam is very precise, and most electrons will strike near the center. However, some will strike the diamond and towards the outer regions, and some will even strike the diamond in this area. Now, if we had a frame, this would be a problem because we would have electrons striking the frame. However, with these very thin tungsten wires, this won't occur. At least the risk of it will be much lower than if they had an actual frame. And as we discussed, the problem is the vibrations, which are translated up through the tungsten wires to the diamond. And the vibrations originate, of course, in the environment surrounding this whole apparatus. And as was stated before, if the electron does not strike the diamond at a very precise angle, the resulting photon will not have the correct polarization. And this is an experiment that requires a lot of precision. So when you have vibrations, it poses a significant problem. Now, the experiment we're using, or conducting, is to study these vibrations. We want to find out in what ways that the diamond is vibrating and also what the frequencies are. And we use this mock diamond setup that you just saw and a laser beam. And we did a lot of theoretical work on this experiment, as Austin discussed. And as he said, we predicted that there could be 4 basic modes of oscillations, or ways in which the diamond could vibrate. Now the first one is motion along the z-axis or the x-axis, so back and forth or side to side. And they can be explained by the same mathematics, so we basically only considered this and explained this at the same time. It can rotate about the x-axis, which means that as the top of the diamond moves towards you, the bottom will move away. And rotation about the y-axis is basically the same principle. However, as the left side, for example, moves away from you, the right side will move towards you. And the final mode, which is very high frequency, because it requires stretching of the wires, will be when the diamond rotates within plane, i.e. the top left-hand corner moves down and left, and the bottom right-hand corner of the diamond moves up and right. Now, as Austin discussed, we are able to make some predictions of the frequencies at which the diamond would vibrate in each of these various forms of oscillation. And you can see those here. And you notice that the z-axis is much higher than the others, and that will be important later, so take note of that. And actually, an interesting thing to consider with these results is that if you notice, all of these first order frequencies, except for this one, are about 60, and that's a problem because there are a lot of things in the environment that like to vibrate at 60 hertz. For example, power lines cause vibrations at 60 hertz, so that's an interesting little problem. And here is the actual experimental setup that we did. And this is called a Michelson interferometer. And this was actually used by two gentlemen around the turn of the 1900s of the century, called Michelson and Morley. And they did an experiment that actually confirmed Einstein's theory using a similar setup. Now we're using it to study the vibrations of the diamond, you know, here. And I have a little animation. And if you'll notice, that is the red dot you can imagine as a photon, and this is the path it will follow throughout our experiment. And the laser beam is actually green, but red shows up a bit better. And the basic process works like this. We shoot the laser beam from here, and as it passes through these two devices, the beam gets kind of cleaned up and expanded from a very narrow beam, sort of like a laser pointer, to one that will cover the entire glass plate. Now here we have a mirror. This laser reflects off the mirror and enters this cube-shaped prism here. Now, as you can see, the beam at this point will split into two directions. The first beam will travel here, which is another mirror, and subsequently the light gets reflected back to the cube and into the camera here. Now, the other beam gets sent towards our diamond here, and the light from this reflects back into the camera. So you can see that you have the unaltered beam reflecting back into the camera, and the one reflecting from the diamond, which goes into the camera, which creates an interference. And when we study the pattern of these two images, we can see how the diamond is vibrating and the frequencies. And I actually have an example of what you can see with the camera. So this is actually what the camera sees. And due to some difficulties, including getting all the parts together, we didn't get as far in the experiment as we would like, but we did get some preliminary results. And if you notice here, this appears to be the diamond oscillating at somewhere between 40 and 50 hertz. And this image is actually slowed down 40 times. So this oscillation is much faster than it appears to be. And this is the sort of image that we have to work with. And from this, as I said, we can learn the frequency of the vibration and which mode of vibration. And as you can see, the experiment is going to be up and running, and we'll have some results. So that is a good thing. Okay, so now I'm going to talk about simple effective theory. And this is very important when we're studying quarks, as we'll discuss in a minute. But I'm going to discuss it as it relates to, say, some more classical physics first. And an effective theory is an approximation. And it includes an appropriate number of degrees of freedom, which may sound a bit confusing. However, that simply means the number of parameters upon which a theory depends, i.e. the number of variables in your equation to describe motion, for example. And we choose an energy scale or a length scale, but what we're really interested in here is a frequency scale. And when we choose an effective theory, we ignore degrees of freedom at higher energies, or in our case, higher frequencies. So it's a lot simpler to work with a theory that is an effective theory. However, we lose the power to predict, say, higher frequency motion or higher energy motion.